All right, everybody. Here's a problem that somebody asked me to do. Let's see what we got here. Agent Arlene devised the following method of measuring the muzzle velocity of a rifle. All right, that's pretty cool. She fires a bullet, and they tell you the mass of the bullet. They say the mass of the bullet is 4.468 kilograms. All right, it's resting on a smooth surface. Smooth surface just means that there's no friction. Okay, it's attached to a spring with a constant of 142.7 newtons per meter. And then, oh wow, I said, something weird. I said that the bullet was 4.68 kilograms. I'm wrong. It was the block. The block is 4.68 kilograms. My bad. The bullet's mass is 7.87 grams. All right, and it remains embedded in the wooden block. Okay. She measures the distance that the block compresses the spring, and then from there, she's able to measure the speed of the bullet. So we want the speed of the bullet. Okay, so that's our data. So let's see if we can get a feel for it. There is a block sitting on a table. All right, there's a bullet that is shot into the block. I'm gonna put a little arrow on the bullet because that's the speed of the bullet. Let me pull that out. Let me move the arrow. There's a bullet with the velocity. We want to figure out the velocity of that bullet. When the bullet hits it, we know that this block is connected to a spring like that, and then we know the spring constant. So that's beforehand, and then we're going to say, put a little b for before, and then we'll say after. So we're going to say the bullet is now in the block because it is embedded, and it's going to shrink the spring, okay? And so we know that there's this distance there, and we're going to say shrink or compress. Shrink or compress, whatever. It's the same difference. And so with all that, we need to figure out the speed of the bullet. So this is what we call an energy analysis problem or a work energy problem. We have to understand a couple things. So there's a spring in this problem. That spring's going to have an energy. The bullet is moving. We're going to have a kinetic energy associated with the bullet. And so that's pretty much the only thing that's happening. This mass in the beginning is sitting still. So because the mass is sitting still, it doesn't have any kinetic energy. Okay. Some people say it would have a mass energy or a potential energy, but here's the thing. If I say that this is going to be a height of 0, then I can say that this mass has no potential energy. Okay. And so with that being said, there is no potential energy in this problem, and we can work it. So we're going to compare the before to the after. So we'll say before compared to after. And this is actually how I like to solve these problems. What I'll do is I'll say before versus after, and I'll put up a little chart. And so I'll break the chart into 4 rectangles, and 3 of the 4, all right, I'll cut in half. And so I'll say this top box is for the work, and I'll say this right here is, sorry, not a T. I'll say this right here is the kinetic energy. I'll say this is the potential energy due to gravity, and I'll say this is the potential energy in the spring, okay? So we got the energy of speed, the energy of the height, and the energy of the spring. And all of those have to be equal to what's called work. If you have not seen work in class, don't worry about it. That's because in this problem, there is no work being done, okay? The reason why there is no work being done is because if ever the whole motion of the situation is due to a spring or due to gravity, then you're good. So in this case, we got this velocity that comes in, it hits the block, and then the spring compresses. But there is nowhere mentioned that someone else did something. So they're not saying, there's a guy pushing it. They're not saying, oh, there is friction. In fact, they told you that there was no friction. They actually needed to say that, okay? So because there's nothing external, like external to this whole thing, this is being my system, because there's no guy on the outside putting any excess force, then all of this is considered to be no work. There's no work being done here, all right? So all we have to say is the energy in the beginning of the system equals the energy at the end of the system, okay? So B, the energy of B equals the energy of A. Ergo, there is no work. So we know the kinetic energy of the system. The kinetic energy of the block is equal to 0, and the kinetic energy of the bullet is going to be 1/2 mv squared, okay? Where this m is the mass of the bullet. Let me see if I can get a denotation right there. So I'll make this pen a little bit thinner. I got 1/2 mass of the bullet v squared. All right, cool. All right. Then what's going to happen is when the bullet hits the block, all right, and the thing comes in and it shrinks, this is going to be the max shrink. And at max shrink, the velocity equals 0. You got to think about it. The bullet's going to come in, it's going to hit it, bang, and then it's going to slow down until it stops. Okay? And that's going to represent the situation at A. So, with all of that being said, you have to understand inherently that the kinetic energy of the system, both of them together, the bullet and the block, since they're the same particle now, all right, since they're absorbed each other, or the block absorbed the bullet, excuse me, they're both not moving. So we know the energy at the end of the system is 0. There is no gravity because we established that the height was 0. And we know that the energy stored within the spring in the beginning, since the spring is attached to the block's not moving, the spring is not stretched. Bam. Okay. So, with that being said, we know that the energy stored in the spring is 0. They don't say anything. If you look in your original problem statement, you got to look to see if the spring was initially stretched. They never say that the spring was initially stretched, which means that the spring has no energy from the beginning. But we do know this. The spring is going to stretch this shrink distance, okay? And because of that, we can now look at the energy stored inside. I know the energy in the spring is 1/2 K delta L squared, okay? So I like to fill out my chart. This chart basically for me is going to represent all of the energy stored in my system. And so now I have a good working understanding of everything of the system. And so here's how we work this chart. All you have to do is say all the B's plus my work equal all the A's. That's going to be our generic way to analyze this system. So all of the B's, you have to add them all up. All I have for my B is 1/2. All right. And that's going to be the mass of the bullet. We know the mass of the bullet is, what's the mass of the bullet? 7.87 grams, which is going to be 0.00787. That's the mass of the bullet. The velocity of the bullet squared, which is what we're looking for, and it has to equal, all right, mind you, there's nothing here because all the other terms are 0. No work, no potential energy, no spring energy. It has to equal all of the A's added up. So we'll take all of this piece right here on the left, and then we'll take all of that piece right there on the right, okay? And so all of the right guys are going to be 1/2. The spring constant is 142.7. So I'll put 142.7. And then I need delta L squared. I know that this spring is going to stretch 946 centimeters, which is going to be written as 0.0946, because remember, you got to convert to meters and you square it. Okay, that's not much at all. Like that is nothing. So this velocity is going to be based on very small energy. All I have to do is solve it. Mind you, there is no gravity and there is no kinetic energy left. Okay, so what they could have done, they could have made it more complicated. All right, mind you, if you look in the problem statement, they said maximum distance. All right, they didn't have to say that. They could say, oh yeah, you know, after the block has stretched. They could have been like, oh, after the block is stretched like a centimeter, you know, what's the velocity? And if that's the case, then we would have had a whole different ball game. But because it's the maximum shrink, we know that the maximum velocity is 0. If you don't know that, you're done. You're done. So with all that being said, that was just like an aside. All we have to do is solve for velocity. The 2's are going to cancel. The 1/2's are going to cancel, excuse me. And so all I have to do is divide both sides by 1/00787. All right. And I'll just divide 0.00787. It cancels over there. And so I'm going to get v squared equals, in fact, I know it's going to be squared is going to turn into a square root on the other side. All right. So I got 142.7. And then I have 0.0946 squared. And I divide it by 0.00787. That's going to be some number. And it is, let's see, 12.738. That's going to be meters per second. Honestly, that's not fast. I didn't expect that. These are some weird answers. I expected that to be like a couple 100 meters per second. Because think about it, bullets move really fast. This is not moving fast at all. Actually, it actually makes me want to check it to see if it's right. Let's see. So I know that the energy of the bullet is all that comes in. This thing is not stretched at all. Yeah. I know the spring constant of a small mass, very small mass, and a pretty small spring constant, honestly. And so I'm not expecting too much, but then it only compresses by a small amount. These are all small numbers. It's just so strange because normally the velocity is like 200, 300, 400, 800 meters per second. But the bullet's going to come in. It has all of the energy of the system. All right. A lot of students go, well, what about the mass of the big block? Turns out you don't need it. All you have to do is look at the energy stored in the little block, and it has to equal the energy that goes into the spring. The little block directly correlates to the spring pretty much. Okay. Well, what about energy dispersing? Energy dispersion is not something that the energy equation cares about. All it cares about is how much is there. How much it disperses is not important. All that matters is how much is there. So the bullet's energy is going to go into the block, but then it's going to become the spring. And so, yeah, no, based on that, the perfection of this system, this is all we have. It's just a small amount of energy. It's just a small amount of energy, and that's weird. If the spring constant were higher, this would make a lot more sense. Like if the spring constant, if this were even, if that value were like 1.4 kilonewtons, yeah, then we'd be talking. But for some reason, they made the spring constant small, and because the spring constant was made small, the velocity is going to be this tiny value of 12. If you want, you could try to make the spring constant 1,000. If you make the spring constant 1,000, this is going to scale up by quite a bit. But, comme si, comme ça, it be like that sometimes, I guess. So all in all, that's the answer. And I'm sticking to it. So if that be that, then I hope this helped.